Okay, today we're going to start some material on Chapter 7, Section 1. And this deals with rational functions, multiplication and division of rational expressions. And this material relates to Math 1109. And there are other topics too, but they were included with the 103. There's a little overlap in topics. And for this, we're using our little booklet, Math Zone. And there are additional exercises in these booklets here in Math Zone. And the answer key is there, and a lot of these are related to our integrity classes that we have in Blackboard. So our first topic here is to find the domain. And if you remember from an earlier chapter, the domain in an ordered pair, well, I can use a parenthesis here, are the x items. So here we're trying to find which value of x will allow these expressions to be working in a math setting. And as we look at this first one, we're wondering what value of x would make this denominator a 0. Because, as you recall, anything divided by 0 is undefined. So we're looking for values of x that would make this expression undefined. That is, what value of x would make this denominator a 0? Well, we say that x, if it were 0 itself, then it would make this expression undefined. So when we write this, we can write it as sort of a set. We can say x is such that x is any value, but x cannot be equal to 0. So once again, we're looking for a value of x in the denominator that would make it a 0. Because if it were a 0, it would be undefined. So how about this one? And you might say, well, what would be a strategy to do it? And this relates to the chapter we've just covered, where we are solving quadratic equations by putting them in standard form, equaling them to 0. But we're just interested in the denominator, not the numerator, just down here. So if we solve this little equation, we say that x is negative 3. That is, if x, we just transpose the x, or the 3, if x were a negative 3, that would make this denominator a 0. So once again, it's something like this, and I probably have not written it correctly. X is such that x is any number, but x cannot be a negative 3. That's better. This one probably should be written like this too. Now in example 3, again, we're not interested in the numerator, just the denominator, and it happens to be in factored form. And we're going to then equal it to 0. And we know then that x cannot be a negative 4, or x cannot be a 4. Because if it were negative 4 here, it would make the denominator a 0. So again, writing this one out, you'd say x is any number, but cannot equal -4, or a +4. Because if we had these values in the denominator here, it would make our denominator a 0. Now as we look at example 4, again, we're not interested in the numerator, just the denominator. Well, what technique would we have? Well, we want to equal the denominator to 0, and then now we have an equation in standard form, and we factor it. And since we need a positive there, those are our factors. Now what do? We equal each of these factors to 0, and here x will equal a +1, and x will equal a -7. But these are the values we have to exclude. So again, for this one, we would say that x is any number, but x cannot equal a 1 or a -7. Again, when we try to find a domain of the values of x, it would include any number except those if you put that value for x in the denominator would make the denominator a 0, and that is undefined. Now as we look at our last example, example 5, again we're only interested in the denominator. And notice our denominator doesn't have x. So for number 5, you would write that x is such that x is any real number. There are no exclusions because there's no variable in the denominator. So this is the first part of chapter 7, and we'll pick up and continue with other examples. Okay, as we continue on into section 1 of chapter 7, we're now asked to simplify rational expressions. And often a synonym, or a word that means the same as rational expressions, is fractions. So these are all fractions. Now in this first one, we're just going to do some simplification through canceling out common factors. So 6 goes into there once, 6 goes into there twice, and remember there are exponents of 1. We bring that up, this will just become then a 1, this will just become a 2, and our answer here is going to be 2x y to the second. So we're just simplifying by canceling out common factors. Now an interesting thing can happen here. If I put that in parentheses, I can always factor out a 1 from anything. And now I see I have the exact same thing divided by the exact same thing. When that happens, all that's left is 1 over 1, and we just write 1. Now here, again, it's going to get more difficult as we move on, but we're showing you more complex examples as we move on. You look at this and you say, is there a common factor in these two terms? And the answer is yes, there's a 3. So if I take a 3 out of there, I get 2x plus 3. So I'm taking a 3 out of each term, and I get this. And now, keep in mind, we now have a common factor of 3 that we can cancel out. So our final answer there is going to be x over what we have left, 2x plus 3. In number 9, this is a really important one. As we look at this, we see there's an x, there's a 7, there's an x, there's a 7, but the signs are different. So if on this bottom one, I take out a -1, I can reverse the signs. This then becomes a -7, and I can put it there, and this becomes a positive x. And now, note what happens. Again, I can take a 1 out of the top one. So what I did is I reversed the signs and also reversed the order, so it looked like that. Took out a -1 to do so. Now these cancel out, and I have a 1 over a -1, which is -1. So this is a technique we're going to use quite a bit in later sections, where we have to take a -1 out of something to reverse the signs, and then have it be able to cancel out with something. Now in number 10, when I set this up, this was all over this one denominator. But the technique for this is to put, when you have like a binomial divided by a monomial, is put the monomial under each term. So this is sort of the second step. And now I'm going to cancel wherever I can. So 6 doesn't go into 17. And I'm going to just check that I copied that answer correctly there. Yes, that example is correct. So we're going to get here 17 over 6. Now the a's will cancel out. One of the b's will cancel out. And that's this part. Then I'm going to get a negative. 6 goes into 12 twice. A will go into there, subtracting, we get a to the second, and the b's are just going to cancel out. So there's the answer for number 10. Now for number 11, and they're going to get more complicated as we move on, we say, can we factor something out of this numerator? And the answer is yes, we could factor out an x. And can we factor this denominator? Well, if you recognize it, it's a perfect square trinomial that will factor into a binomial that we could write it squared. Here we're going to prefer to use it in the traditional form, so we see them separated, because now we have a common denominator and, well, a common factor on the top and on the bottom. So now we're left with this x over this one. Now, I tried to put a lot on the board, save a little bit of time and room, but again, when you do these, you have to develop a way to keep track of what you're doing. Sometimes I would use a different color for this step. I didn't here, though. One other thing. Can I cancel this x with this x? And the answer is no, because this x is a term, and these are two terms, and you can only cancel out factors, not terms. So no, you cannot cancel out these x's. That would be wrong.